So far, we have studied the ordinary least squares regression. But you remember that we began by saying that the assumptions of regressions like normality, homoscedasticity, multicollinearity, autocorrelation, endogeneity, and several other things. And some of these assumptions must be cleared before you know your model is correct. That's the purpose of today. So I want to look at the first assumption, which is multicollinearity. What is multicollinearity? Multicollinearity exists when two independent variables are so highly correlated that it's difficult to disentangle the partial effects of one of these independent variables on the dependent variable. Okay, so when the independent variables are so highly correlated, it becomes difficult. And multicollinearity is said to be a case sometimes. When you have the presence of multico, the OLS estimator will be unbiased. But an unbiasedness is good, but they will not be blue. They will not be blue means that they will not be best linear unbiased estimators. They will have large variances, okay, and large standard errors. And you know that the estimate divided by the standard errors will give you the t statistic. So it means that the coefficients are likely to be insignificant in the presence of multicollinearity. One of my PhD students is doing some course and she's struggling and does not understand why some of the independent variables she was expecting them to be significant are not significant. Apparently, there were a number of, she's not even tested for multicollinearity. So it's important that you do that. If there's a presence of multico, you can commit type 1 error. And some of the papers I'll give you, you would have seen that they have committed these errors. You will still have a bigger R square. That tells you that the model is well fit, and yet the coefficients are insignificant. So multicollinearity is a big issue if they are quite enormous in the data. So let's remind ourselves of the correlation matrix, and let's remind ourselves which variables were multicollinear. Please, who can tell me which variables were detected to be multicollinear in this correlation matrix? We have the quantity demanded of gin bitters, the price of gin, the complement price of gin, income of the people, location of the shop, occupation, teaching and trading, religion, Christian and Muslim. And we created this correlation matrix. Who can remind us which pairs, 3 pairs of variables were identified to be multicollinear? Who can remind us? Yes, who can? Which variables were identified to be multicollinear? Martin,
I think price and complementary prices.
Price and complementary price. Yeah, they weren't the first identified to be multicollinear variables.
Sorry, price and OTR.
Why? Why do you say that?
Because the correlation between the two variables is the highest so far.
What is it?
I mean, the independent variable, the correlation between those two independent variables seems to be the highest.
Don't say seems. Based on the... Don't say seems, because we are looking at everything here, so you will know.
It's
what is it? What is the value?
It is 0.76.
Mm-hmm. And it is what? It seems to be the highest so far.
Yeah, yes. In terms of ranking. No, it is.
Okay.
It is in terms of the ranking.
And which is the next one?
The next one is price and complementary price.
I know you wanted to say that one. And then the next one.
We have I think LU and RC or LU and OTR.
What's the value?
0.65.
No, that's not correct. So you've done something. Let's go to another person who can tell us the next one.
Yeah, we have the income and then the consumption.
Please tell me the correlation and then why. What?
The correlation is 0.71 for consumption and then income.
Okay, so first of all, it's not consumption. We've been using this data all along and we called it complementary price. So I thought you knew. Second of all, the 0.71 is not correct. So another person who can come and correct it. James. Follow me.
Yeah,
most of you are not following. You're not paying attention.
M and RM. M and RM, negative 0.73.
Okay. So that is a correct one. Okay. So these variables were the variables that were identified to be multicollinear. Now, how do you handle it? First of all, how do you check it? How do you detect the presence? One way you detect the presence of multicollinearity, ladies and gentlemen, is to use the variance inflation factor. The variance inflation factor measures how the variances of the regression parameter estimates are inflated because of collinearity. So that means that the variables that are causing the multicollinearity, the independent variables, we got to know the VIF for each one of them. The VIF basically is just 1 over the 1 minus the R squared. And the rule is that if the VIF is bigger than 10, then there is high multicollinearity. In fact, if the VIF is 1, then it means that there is no correlation at all, between the predictor. And therefore, the variance of that beta parameter is not inflated at all. But if it is bigger, exceeds 5, or is, it's close to exceeding 5, then we seem to say there is a moderate, variance inflation factor. So then there is this issue of, moderate multicollinearity. And if it is 10 or bigger than 10, it shows signs of high multicollinearity. Who can tell me this? What do you think is the variance inflation factor in a simple regression? Who can tell me? What do you think is the variance inflation factor in a simple regression, and why do you say so? I got 2 hands raised. So let's give it to Mami Fosu.
Please, I think it will be 1.
Why?
I think it is 1 because we are saying that if there is no correlation between 2 predictors, but in this case, there will be no other predictor. So
yeah, so
if there is no other predictor that there will be a correlation with, then there will be no multicollinearity in the model. So then the variance will not be.
That's it. That's it. Okay. So, ladies and gentlemen, first thing, let's go ahead and check whether there's a multicollinearity in our data set. Okay. So I'm taking us back to our regression. And for your information, down here, when you look into the regression, you will notice that I have the regression estimated already. If you have yours, you can follow me. This is estimated regression equation. Okay. We want to check for the presence of multicollinearity. And to do that, I'm going to do something very interesting here. I'm going to install a package known as CAR. If you have that CAR package installed already, you don't need to install it. So this command here is CAR. I'm going to load that package first because my goal is to get the variance of the variance inflation factor. So let me load the package. I hope you can see my screen, my R screen. Okay. So the next thing is to type VIF, then the name of your data. So you type car A, car column, then VIF. I hope you see my screen. You see my R screen?
Yes, we do, bro.
Yes, we do.
So once you run this command, it is going to give you some beautiful variance inflation factors. That's the result you have down there. But this result, if you don't take care, you will not fully understand. So let's go further to find some few things. We are going to command R to tell us, okay, that drop the independent variable whose variance inflation factor is greater than 10. So let's run that. So that is what you have here. All of them are in a very cool shape, as you can see. Okay. Let's take the square root of that. In other words, we are asking R which independent variables are problematic. Let's run this command 165 to ask R. And it's telling us here that none of them is problematic. So all of them are false, 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 false. None of them is problematic. So it means that the independent variables are not showing real signs of problem. But watch something. There's something interesting that you have to take note of, because the information that you're having there is quite strange information. The variance inflation factor you are seeing here, it doesn't, if you don't take it, you don't understand, because there are two information that is given. So let me just give you a bit of an idea into the information you're seeing. Do you see that one of them is GFIF, and then another is GFIF to the power 1/2 times degrees of freedom? Okay. The GFIF is known as generalized variance inflation factor. That one, the generalized variance inflation factor, the one I've highlighted here. That is the GVIF, the generalized variance inflation factor. I'm making the screen bigger a bit so that you can see. It was actually postulated by Fox and Monette, 1992. They brought about that model there. And it is a dummy independent variable. Okay. It's a dummy independent variable, so it's for polynomial variables. Now, polynomial variable, if the variables are continuous variables, take note. By the way, when we say continuous variables, they are different from discrete variables. Continuous variables are variables that can be decimals, like age, height, money. You can add all this to be decimals. But variables like gender, sex, yes or no, true or false, these variables are discrete variables. Basically, discrete variables are like whole numbers, and continuous variables are like numerical variables. And then discrete variables are like categorical variables. Now, if the variables are continuous, then the generalized variance inflation factor will be equal to the variance inflation factor. Pay attention here. If it is continuous. But if it is categorical, okay, then we get one generalized variance inflation factor value for each dummy variable. So for example, you will get one value for all the age groups. Suppose we have age groups. And these are ages. They are all ages, but we have them in groups. So you're going to get one value for all the age groups. So ladies and gentlemen, check carefully and you'll see location. Do you realize that location has got two levels, isn't it? Are you aware? What are the two levels for location in our Brukutu data set? What are the two levels? What are the two levels? The two levels, yes, Robert.
Sir, sorry, I didn't raise my hand.
Urban
and rural.
What are the levels for occupation?
Occupation, fishing, trading, and teaching.
And religion?
Yeah, and religion. Religion, Buddhist, Christian, Islamic.
Okay, so what do you notice about these categorical variables and then the numeric variables? You will notice that for the categorical variables, okay, you had all of them being given one generalized VIF. Do you realize that? All of them were given one VIF score. So if it is religion, all the three religions were given one VIF score. So variables which require more than one coefficient, and therefore more than one degrees of freedom, they are typically evaluated using the generalized VIF instead of the VIF. This is the point I want to make. So if you have dummy variables in the work, you want to use the GVIF instead of the VIF. Simple. But if all of them are numericals, then using the VIF is no problem. Number two, there is another column, which is the GVIF to the power something. That's second column. Okay. What does that mean? By the way, the degrees of freedom is showing the number of levels. Sorry, the number of dummies. So occupation, for example, is 2. Religion is 2 because he's telling you that he formed 2 dummies. That last column, what does that mean? That last columns, you know, the two guys, Fox and Monet, 1992, they suggest that that last column makes the value of the GVIF more comparable across dimensions of different betas. They are more comparable across different betas, different beta parameters, which reduces the GVIF to a linear measure. Even if some of them are not linear, it reduces them to a linear measure. So basically, ladies and gentlemen, it is analogous to taking the square root of the VIF. That value you see that last column there is analogous to taking the square root of the VIF. So what is the essence? In fact, what is the difference between that column GVIF and the column GVIF to the power 1 over 2 times the degrees of freedom? What is the difference? The difference is that the second one reduces the GIF to a linear measure because the GIF could have polynomials in them. Okay. And so you reduce it. So it's like the GIF is the variance, whereas the one with the square root to the power 1 over 2 something, that one is like the standard deviation, basically. So which one do you use? Which one do you use? Use the second one, okay? Use the second one if there are possibilities of polynomials or there are possibilities of, if you want to make the value of the GIF comparable across different betas, then that is what you want to use. Okay, so what does this tell us? Is there multicollinearity? Well, technically, and basically there's not much multicollinearity, but there's something here that can guide our thought. Now, you guys said that the first variable that shows some sign of high correlation, not multicollinearity. The possible high correlation was between price and which variables did you guys mention? One guy was telling us all of that. Price and what? Occupation, teaching or trading. Check your values and tell me, price or what? Okay, if you check, it was price and occupation trading. So if you check price, okay, if you look at the price just in the first one, it appears that there's a bigger value there. Occupation trading is inside this 80. So it appears that there's some bit of things there. Okay. What was the next one? The next one you guys mentioned was, it was price and complement price. Okay. And you see price is a bit, it shows a bit. Now, the latter one is what you use, which you use to correct those possible polynomialism in the work. Okay. But I'm just using this one, the left one, to just tell you possibilities of multicollinearity that could have happened based on what you selected earlier. Okay. So, but basically for this data, there is not much of multicollinearity in the data set. So how do you handle it if it is there? If an independent variable has a considerable multicollinearity, and let me show you here. Because all of this will come in your final assignment. If an independent variable...
Can you mentioned that there's no multicle in the data there. Can you show like how you came by that?
Okay. So when you look at the last column, the one for the GIF raised to the power, something 1/2 times the degrees of freedom, you will notice that when you check all the numbers, none of them was above 10. I don't know if you can remember. And you can see it from the data.
Yes, I remember. I noticed.
Yeah, none of them was above 10. And when you now commandeered it and asked whether it was showing, is there any multiple, serious multiple, you had false for all of them. Do you remember?
Yeah.
So that false indicating that there is no high multicollinearity in the data.
Because the slide that you showed us earlier was referring to specifically the VIF.
Yeah.
But in the other, but in the R studio thing you showed us, you saw the GVIF raised to the power 1/2 times. So that should make for the VIF.
Yes, that is the one you will use for the VIF, because the VIF is tainted with some other problems in real life.
Okay.
Yes, so the 1 to the power 1/2 times the degrees of freedom, it corrects for that. That is the one you will use.
Okay. Okay, sir.
Benis Fosu, your hand was up.
Yeah, Prof. So I just wanted to confirm that. So if you have a moderate VIF, it means it's nothing to be worried about. Is
Not
that
at
what
all.
it is?
That's correct, yes. You don't need to be worried about that. Okay. Let's move on. So when you look at let's assume that multicollinearity is there. Now I can force some of the variables to be multicollinear, and therefore, they have an issue. But if an independent variable has a considerable VIF, a very high VIF, one way you can handle it is to drop it. But be careful, because if that variable is the one you have written a lot of literature review about it, dropping it will mean that your entire literature review will be thrown away. But if not, a big issue with the literature review on it, then you can drop it. And the model will have to be rebuilt with the remaining independent variables that showed low VIF. That's all. That's how you handle it. Okay? That's the first way that you can use to handle it. You can rebuild the model, and then you can check the p-values of the model. And here is a key important thing, and take note of this, because some of the papers made that mistake, so take note of this. It is not good practice to consider VIF values for dummy variables. Why? Because they are correlated with other categories, and therefore they are likely to have high VIF. So guys, if you can remember, most of the dummy variables we had, they had a high VIF. Yes, Felix.
Yeah, yeah, Doc. When you said if in the event that your independent variable has high VIF, and you've not done manual literature review on it, you can drop it. In the event that probably most part of your work hinges on something that particular independent variable, what do you do? How do you treat it?
Keep it. Keep it.
Compromise would your models to be okay to?
Well, keep it and check.
That high level.
Keep it. Let me just tell you some secret. Let's say you keep it, and when you keep it and you go and run the model, and you pray and hope that it is significant. If it is not significant, find out the reason why it's not significant than just dropping it. Because if you don't do that and you keep dropping, if you don't take care, you'll be dropping everything. So I'm just saying that dropping approach is just one of the approaches that some use. But that is because they have so many independent variables. If your independent variables are not many, number one, and two, you have a strong case that particular variable, okay, so if your variable J is what you have written literature review on, and that J is correlated, obviously it will be correlated with another variable. So it is that other variable which you haven't written a lot of literature on, that is the one you want to down check. Maybe that variable is what is causing your J variable to be highly inflated. Hope you get my answer.
Okay, thank you, Prof.
All right, otherwise you won't have a story to tell. Okay, so take notes, and take note about the dummy variables. You don't look at their VIFs. Okay. And this was one of the questions I think I asked you at some point. Okay. So independent variables with insignificant p-values may be removed and another model rebuilt. So if you want to know whether these variables are a big issue, what you want to do is identify those independent variables that have high VIF, remove them and check. They have insignificant variables. Which variables are those? Go and check your data. Let me show you the data set. Okay, go back to the data set and check which variables were showing insignificant results. Here. Which variables? Which variables are showing insignificant p-values? Do you detect any variable?
Yeah, Prof. Income, location.
Income and what?
Location urban.
Location urban. So location. So location and then income. These are actually problematic when it comes to what? Insignificance. So these are the ones that you want to what? Remove and run the model again. Okay. Now, this is not to say that for our data, we are going to remove this, but I'm saying that if this is a big issue in your work, that's what you want to do. Maybe you wanted price to be significant at 5% or 1%. But right now, if you look at price, it's not significant at 5%. It's only significant at 10%. So maybe when you remove this variable 1, M, and then you go and remove the A band, maybe that will make price significant. Yes, Dennis.
Prof, sorry, but I'm a bit confused because of the little knowledge I have about the VIF. I think O'Brien 2007 made an argument that some of the VIFs that are above either 5, 10, or 30 is also acceptable. So now that we are limiting our conversation to 10, I'm kind of confused a bit.
Okay, so this 10, I'll give you the reference, Woodridge.
Okay.
So several authors have several demarcations. So if you look at your work and you have a VIF, which is 40, and you have an author who have said 50 is better, quote that author and then use it to support your 40. Do you get a point?
Would that still be acceptable?
But you are quoting somebody now. You are quoting somebody now.
Yes,
you are quoting.
in this regard, I'm quoting someone because I feel how do I say I am quoting someone, but I feel you are teaching me what I have to use for my final dissertation. That's what I'm asking.
Quote good references. I don't know the one you spoke about. Quote good references. You see, this is what people do. What they do is that when the thing is not working, then they go and look for somebody who has said something small about it. But if it is in a good journal, Woodridge is a top class authority in this. So if Woodridge is saying that those above 10 are considerable issues, go for that. Go for that. If someone says 40 is good, he is saying it, but he is not that much of an authority than the authority that you are actually, listening to. So I'm saying that it's not, you go with what you believe is the author saying. You see, there's no hard and fast rule. That's my point. The thing can have multicollinearity and yet can be significant. A variable can be multicollinear and yet it's significant. I mean, you remember that we saw occupation teaching was, multicollinear with price. In fact, it was the first high correlation. And therefore, we checked it. And it was also high. But of course, that was a dummy variable. And because it was a dummy variable, you can't use it to judge VIF. No, but look at it. Occupation teaching is what? It's highly significant. Occupation trading is also highly significant. So it is the ones that are insignificant that I would really much more concerned about their VIF than the others. At the end of the day, you still have to ensure that when the VIF is more than 10, you will check it. Okay? You will check it. Doesn't mean you should punish it quickly by removing it. Okay? Remove it, but you will check it first. Removing is handling it. Checking is testing it. Detecting it before you remove it. You see, it becomes a bigger issue to remove if only it is making the other guys not do well. That's when it becomes an issue. It's making the other guys not do well. I hope you get it. Yeah, Venice.
So, Prof, not to take you back, when you test, are you looking at the fact that there will be significance, or are you looking at the fact that the model will have a VIF lower than 10, which you say is acceptable?
Yeah. When you are testing, you are checking the VIF value to determine whether it's acceptable or it's not. When you handle,
thank you.
Yeah, when you handle, you are determining whether to keep it in the model or not. Yeah. All right. There are other tools you can use to handle this whole VIF thing. There are other tools. Let me just take you back to the model in the R. So when you go to the R, and you decide to run this R whole thing, There's another tool which is called J-tools. J-tools is a very powerful tool because as you run these J-tools, and then you now run your regression, and I'm running the regression again, by the way. Watch what you get down here. It tells you the dependent variable, the independent variable, the R square, the adjusted R square, and then it gives you the p-value for all of these. After that, let's run this. You can ask, this is Fox and Monitis, they introduce the result. So when you now tell the R to run the VIF for you, this is what you get. So this one gives you the VIF on the last column. Watch it, on the last column. You have the VIS for each value. And you can see that we've already been saying that don't look at the VIF of the dummy variables. Why? Because if you look at these dummy variables, the VIF are all the same. So that's why we said that for dummy variables, be careful about looking at this VIF. But I'm just using this to just show you that you can have the VIF automatically show in the, what do you call it, in the table, without going to actually run it separately. And that is a J-tools command that can help you to see that information very, 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 very nicely. And again, the paper by Fox and Monet, 1992, it was published in a good journal, a Journal of American Statistical Association. So when you quote that, that will guide you into selecting your VIF. So all the ones I give you are from there. So let me show you if multicollinearity is there, how do you handle it eventually? How do you resolve it? So here's the first point. Multicollinearity, when it is there, it can affect the coefficients. That's one. It can affect the p-values. That is two. But it will not affect prediction or goodness of fit. So if your goal of a regression is to do prediction or to ensure fitness, then multicollinearity can exist as much as it wants. You don't care. Because it's not going to affect your prediction or your R square. It's not going to affect your prediction or your MAPI or root mean squared or MI or any of those. So that's the first thing you want to note. Second point, how do you resolve it? How do you handle it? We've already said it. Remove one of or more of the multicollinear variables. Remove it from the model and rerun your model. Doesn't mean throw it away, just remove it. So that is why sometimes you read papers. Yes, Felix.
Yeah, Prof, you said it will not impact, it doesn't impact prediction. But if the coefficient estimate are impacted, when you are predicting the outcome, won't it be affected?
It will be slightly affected, but the prediction will also have the constant. You remember the constant value?
Yeah,
you remember
the intercept.
Yeah, the intercept. The intercept will also be included to handle all of those anomalies that could happen. That's why we don't pay, that's why we are not too much bothered with that. The impact that could be, the coefficient, the intercept is there to handle all of that question you answered. And remember, when you are actually predicting, you are including everything, you know that. If you can remember the last time we looked at prediction, we said that the price of gin is 15 cedis. The complement price of gin is 15. The income of the people is 20. Okay, and the person is a Muslim trader living in a rural town. All of the independent variables are used in the prediction process. including the intercept. So that will handle it. Okay. So the first is to remove one of the more multicollinear variables. That's the first one. And I said doesn't mean throw it away. It's just removing it and rerunning the model to see what happens. If nothing happens, bring it back. That's all. If nothing happens, if the R square remains as it is, if the coefficients were previously significant, they are still significant, nothing has changed, bring it back. It doesn't affect anything, so you bring it back. The second point is you can combine the predictors in some way. That's a point here. Combine the predictors. For example, you can add or subtract them from one way. For example, you can combine a predictor like education and income. And when you combine them, one way or the other is going to handle the multicollinearity problem. That's number 2. Number 3, you can perform a principal component analysis. That's a whole new topic that you will learn, before structural equations model. Or you can do partial least squares regression. And what they do is that these approaches can handle highly multicollinear predictors. So if 2 predictors are highly multicollinear, you can deal with them that way. So these are the 3 ways you can use to handle multicollinearity. Any question on multicollinearity? Dennis?
Yeah, sorry. Yeah. So I just wanted to find out.
You sound far away.
I wanted to find out. You said in dropping the variable and testing it, do you have to?
Dennis, I can't hear you.
Hello, sir.
Please, can you regulate yourself a little bit because I can't hear you.
Hello.
Yes, go ahead.
Okay, so I'm saying that in dropping the model and testing the in dropping the variable and testing the model, I want to find out, do you have to go to the data and drop it, or is it like a command that can let you hold that, like let you drop?
Oh, no, go to the data. Let me show you. Let me just show you. Your question is an interesting question. Let me just show you. I'm taking you back to the R. Please, do you see the command number 170 that I have highlighted? Let me know if you can see that command. Do you see that command?
Yes, please.
Yes, bro.
Now, if I am dropping this variable m, all I have to do is that I have to remove it from the model like this and cut it out. I just did. Do you see it?
Yes, Prof.
That's it. That's what we mean by dropping it. And now I'm going to run the whole thing again and see what will happen to the result. So right now, let me show you. Remember, it was m. If I run this regression, watch it. Look down here. M is no longer there. M is no longer there. Do you realize that P has become, the P value has gone up? Do you see that?
Yes, please.
P value for P was 5.5%. Now it's gone to 14%. So removing that M didn't help P. That's what it means. Let me take it back. Okay, I'm going to run it this time with M back. And then watch. Now, do you see that P is now almost 5%? Do you see that?
Yes, please.
So that's what we mean by dropping and rerunning. It will help you to know which variables are affected by dropping the variable. And that is how it works. Please, does that answer your question?
Yes, please. Thank you very much.
All right. So let's go back to another assumption, the second assumption. And that is the fact, the assumption is called normality. the residuals should be normally distributed. That is the second assumption of regression. The mean of the residuals should be normally distributed, or the residuals should have a constant mean, okay? Or they should have a zero mean. Let's check it. Let's go to the R. Let's go and run the residuals and check their mean. There's a command that can handle that. There's a command that can be used to handle that residual, the residual weight. Where is that? Okay, so first thing, for small sample sizes, the normality assumption is needed. When your data is small sample, what do you mean by small sample? When it is less than 30, that's when it is small. So when your observation, suppose you collect banks, and the number of banks you collected, or your total observation is less than 30. The number of banks can be 20, but because you collected them over years, the observations are more than 30. That is a big sample. When the observations are less than 30, that's a smaller sample. And for smaller sample, you got to ensure that your data, your residuals are normally distributed. So how do you do that? Let's try it. Okay, there are several ways to handle this normality. One is using the QQ plot, the quantile normal probability plot. That is what you see here. Let me zoom. I'm sure you guys can see the quantile normal probability plot. I hope you guys can see. You see? Do you guys see? So this is a plot where you want your independent variables or your residuals to be seated on the blue line. You want them, all the plots, to be on the blue line. Okay, so you check if the residuals are normal. Now I want you to check, do you notice some observations seems to be not normal or not slightly normal? They are a bit skewed, or they are like outliers. Which observations are those? Do you see 14 up there? Do you see 14 there? Do you see 24 there? So these could be questions, question mark, that you want to really double check them. Okay. Now let's draw even more plots. We want to draw the plot in one box. So let's plot the J multi in command 177 here. Let's plot this J multi. And this J multi gives you all the residual plots that you need. Again, check 24 at the top. Check 24 and 14 and 34. Check 24 and 14 and 34. You will see that these things, okay, are beginning to cause some bit of questions. Now, if you look at this plot here, the first one, okay, if the red trend line that you see there, and you see there is a dotted line, which is horizontal. So if that red trend line is approximately flat and close to that dotted, then one can assume that the residuals are normally distributed. We are just using sketches. You can use more than sketches. Okay. But the best way to check for this residual is to do a Shapiro test of normality. So we want to test if the residuals are normally distributed, if they truly have a zero mean. So you use this command, Shapiro.test, bracket residual, then the name of the data. We want to check whether the residuals are normally distributed. Now, when you run this test, look at the bottom. The p-value is approximately what? 0. So if the p-value is greater than alpha, then they are normally distributed. In this case, the p-values are not greater than alpha. So it means that they are not normally distributed. And I know some of you, your question will be, so how do you deal with it? Okay. Now, one way you deal with it is by using something called transformation, and we'll look at that later. Sometimes you just have to take the log of some of the variables and to correct it. Okay. So that's it. Another way you can test for the residual is this. Load this data set, this package called OLSRR. All of these things I'm showing you are in your slides, by the way. OLSRR. Let's do that. Okay. And then run the command number 180 here, which says OLS test normality. So we want to test if the model is, the residuals are normally distributed. And this is a fine result you get. Look down here. I love this result because this result will tell you for each one whether the data is normally distributed. It's beautiful. If you can interpret it, is beautiful. Okay. What do you see? First, you will notice that the Shapiro work is saying that the data is not normally distributed. The Kolmogorov-Smirnov appears to show that it is normally distributed. The Kramer-Von message shows that it's not normally distributed. Anderson-Darling shows it's not normally distributed. So you got some that are indicating that it's normally distributed, and you got some that are not indicating that. What do? Take a decision. Choose the one you want to choose and take a decision. Or you can go ahead and correct or re-specify the model. We'll look at how to re-specify the model later. These diagnoses are very important. Okay? And it is important that you understand this so that you use them to criticize the papers you are getting. So what are the key points that I want you to take home for the normality? Number one, normality of the residual is only required for valid hypothesis testing. This whole normality assumption, it only assures that the p-values of the F and the T test are valid. So if you go and check the T test, you see, this is our data. The F test was valid. Most of the T tests were valid. That is why I'm being slow about it. There's another data I'll give you, and you will have a lot of invalid work. And you'll see that one way to correct them is by handling some of these diagnostics. Next point, the OLS regression will just require that the data or the residuals are independently and identically distributed. If you have outliers, if you have small data, all of these can cause non-normality to happen, which will lead to misspecified errors or nonlinear variables. So that is why I told you that. So it is possible that if you have a lot of non-normality, it means you misspecify the model. The model we used was an OLS regression. So maybe, just maybe, you don't need to use what? OLS regression. That's what it means. It means that you may have to use a different kind of regression than OLS, maybe a nonlinear regression. Please note also that there are other ways you can check for normality. You can use the kernel density estimation. We have already mentioned the quantile normal probability plot, the Q-norm, and then the P-norm plot. You can use all of this to check for the normality of the residuals. So what if the residuals are not normal? Like in our case. Well, in our case, they are not normal, okay, like in our case. How do you handle it? Watch. You can handle it by you. So instead of going to even say that, ladies and gentlemen, I have to check whether the residuals are normal. You don't even say that, just correct it. If it is there, it will be corrected. If it is not normal, the non-normality will be corrected automatically. If you do what? If you use heteroscedastic corrected covariance matrix, don't worry, it's part of the game. to know some of these things. There are about 7 of them, HCO all the way to HC7. Any one of them, you can try them by iteration to see which one. So you can use this in the model, in the estimation process. I will not do that now. I'll do that when we come to heteroscedasticity. If you do that, you can correct for the non-normality. That's 1. 2, you can do bootstrapping. You can bootstrap according to Efron and Tibshirani. You can do bootstrapping, and the bootstrapping will create multiple pseudo samples. Okay, you resample with replacement, and as you resample with replacement, you increase the size of the sample. You create artificial data to increase the sample size. I see the data, and you know that normality is as you are increasing the sample and increasing the sample and increasing the sample and increasing the sample. Eventually, you are going to make the data or the whole situation normally distributed. That's another way. A third way is by trimming and winsorizing. This is known as robust regression. You can use robust regression to handle normality. Another is logarithm transformation. As I mentioned it some few minutes ago, transformation. How? You can take the log of the Q variable. Our Q variable was quantity demanded. You can take its log alone. And I'll show you an example very soon. Or you can square some of the independent variables. Okay, that will be another way to probably correct. Or you can take the exponential of some of the variables. Another way is by using non-parametric methods. Okay. Another is by using nonlinear models. And these all of these nonlinear models, we'll look at them. Weighted least square, generalized least square, feasible generalized least square, two-stage least squares, generalized linear model. All of these are nonlinear models that can be used to correct for the non-normality. My preference is the first one. Run the OLS, incorporate HCO or HC7, any one of them between 0 and 7, and then you can correct the problem. Any question on the normality point? Because we are going to another one, which is known as linearity. Ensure that there's a linear relationship. If a paper is not doing this, you got to penalize the paper. Next one, let's go to linearity. Regression diagnostic called linearity of the variables. Let's check if the variables are linear. Each variable, let's check. Let's go to our R. How do you check for that? You can use this command known as crplot on your model. Our model has always been gen multi. So we are going to create something called crplot. Crplot simply means component residual plot. It is a very good way to see if the independent variables have a linear relationship with the dependent variable. One by one, we are checking each one of them one by one. Each one by one. Let's run it and see. Okay. Now look on the right. One by one. So we take the first one. The first one was price. Look at price. Price alone. Price alone. Okay. This is price alone. So if you look at price alone here, what do you see? Do you see that there is a linear relationship between price and, the quantity demanded? Yes, it appears. But you see, a bit of the deviation is from the pink line and the blue line. That's where a bit of the deviation is. So this is plotting the residuals against the fitted values. And it will ensure the residuals don't form a strong pattern. That's a key point I want you to note. We do not want to detect a strong pattern. Okay. Models residuals with one independent variable against the dependent variable. And then it will add the line of best fit to it. Okay. So If you have a significant difference between the residual line and the component line, it will show that there is a non-linear relationship between that independent variable and the dependent variable. So look at the blue line, okay, and then look at the component line. Okay, the blue line, what is that? And then the component line, the residual line. If you check for price, it appears that they are kind of almost similar. If you check for complement price, it looks like there's a bit of deviation at the middle. If you check for the income, there's a bit of deviation slightly at the middle. As for the what do you call it, the dummy variables, we cannot even use a line for them. We have to use box plot for each one of them. Okay. The residuals should not form a strong pattern. That is what we are expecting to happen. Okay. So do you sense that there is some non-linear relationship somewhere? You guys see? If you check for the linearity, the residuals are plotted here against the fitted line. Okay. If you check any of these plots, do they show any systematic shapes? If they do, then the linear model is not appropriate. That's what we are saying. So it means that you would need some non-linear relationship. And when I say non-linear, what it means is that, you know, in fact, this graph is fine, but it's not showing better stuff. Let's go to another graph. Look at the next graph. The next graph is even much, much beautiful because it takes each of them. Remember, I told you that for the dummy variables, we don't talk about them. Look at the numerical variables. Look at between price. Okay. If you look at price, it appears that there is some bit of linearity. The most important thing is that if there is some pattern in the fitted values and the residual values, in other words, if the residuals are not randomly distributed, we can fix that. It means that there are no, what do you call it, linearity. And so we have to log transform the data on the dependent variable. And I will do that very soon. Okay. So let's check. Look at price, and then it appears that the blue line is supposed to sit on the black line. Slightly, maybe not, it's not. But it looks better than the complement price. Look at complement price. It's even showing a parabola. Okay. It's showing a sort of a quadratic graph. If you check income, it's similar. It's showing a bit of a quadratic graph. Okay. So it appears, I'm just saying, it appears that these independent variables seems not to be showing a clear-cut linear relationships. It appears that the concept of linearity must have been broken down. It appears. How do you check or correct that? Ladies and gentlemen, one way to check that is by log transforming the data. So look at this command here. You're correcting it. You're correcting it. You do gin, and then instead of kill, we now do log of kill. I'm creating a command called log of kill. And this log of kill is inside the gin. Okay, I'm creating it inside the gin. Okay, let me show you the gin data below. Look down here. Oops. Look down here. Okay, you can see the log, the entire data set. Okay. Okay, now I'm going to add the log of gin. So I'm going to run this command here. And let's see this log of gin. So I have created another data by taking the log of the quantity demanded. Remember, this was the quantity demanded. Look at the first variable. It was 160. Okay, the second variable was 200. The third was 160. The next was 220. What I have done here, and look at it, is that I've created a log of each of these. So the first the second, the third. Okay, I've taken the log of all of these variables. That's what you are seeing there. And now I'm going to run the regression using that log. So watch it. Watch it carefully because this is a beautiful thing. And this is a best solution, one of the best solutions. So if I go to Jim, let's look at Jim now. Look at the last column. Because I've added that variable, look at the last column of the Jim. Do you see the last column, log of K has been added? Hello? Are you with me?
Yes, sir. Yeah.
Okay, so you have that log of K added to the data because using the K may have some bit of non-linearity. Some of the variables, some of the independent variables may have some bit of non-linearity. So we take the log of the K. Now I'm coming to command number 188 here. And I'm now going to run the regression model, this time not with K, but with the log of K. Watch it and note what happens. Let me run that. And look at the results now. Guys, who can tell me, what do you see between this result and our original model we had? Who can tell me? Who can tell me? Who can tell me what do you feel, what do you sense about this model and the original model we had? You don't sense anything? Come on, you should sense something. You should feel something, sense something. What is your first observation? Yes, Ebenezer Nyako.
All of them are significant now.
Okay, unlike previously, what?
Unlike previously, where some of the independent variables were insignificant, like
Good.
M.
Very good. Like M and then location urban. Okay. What else do you observe? What else do you observe about the p-value? Okay, let me show you the previous one. Oh, not this one. I wish I can show you the previous one to see. Let me show you the previous one. Okay. So that was the previous one. Let me show you. Let me compare. Let me juxtapose each one of them and then compare so they can fill it. So look at the previous one up here. Okay, and then look at this. What do you sense about the R square? Can somebody see something about the R square? And then adjusted. There's something slight about the R square and adjusted. What do you see? Or you guys don't see? The R square
They appear to be the same. They are almost the
it's
same.
not the same.
No, the adjusted R square.
I said they are all not the same. Comparing the two models, what do you see about the R square? Slightly speaking.
Well, please, can we see the other model now that we've seen this one?
The other model is up here. The R square is up here.
It's like it's increased a bit. No.
It's not a bit. Maybe your language of a bit.
Yeah.
It has increased. It has increased. It's because you are rounding them, so you are not seeing.
Yeah.
It has increased. So the R square has improved. So this means that this model of using the log of K is a seemingly better model than the previous one. Look at the independent variables. But you have to be, of course, careful in interpreting the scores because we are dealing with log. This is only to show you. Now we are going to go and check the residuals. Remember I told you to check whether they are linear. Now let's go and check whether they are linear now. So I'm going to do the same residual and component plot on this one. Look at the command number 189. Because the one that you saw earlier is what you see on my right here. This one on my right, this picture. That's the old one. Now let's do this new one, the one we took the log. Do you realize that price seems to be seated now on the blue line, unlike before? Or it's only my eyes that see? You see that? And let's look at a component plot. The component plot doesn't show much, but then the residual plot, this one, it shows a bit of a straight line than before, isn't it?
That's correct.
Yes, please.
Good. So that's just to prove to you that just by taking the log, just by taking the logarithm, can do much difference in the result. Okay. That's basically the point. Can do much, things in the results that you want to really handle. Very, very good. Any question? Yes, Asagibi.
So I just want to find out, when you just log, is it okay to just log the one side, the kill, just because can you log all? Decide to log all.
So that leads to a story on when and when not to log. So the first thing you do, the logging is in the process, and each one must be justified. You log, if you can remember the first one, maybe when we come to panel, you'll understand. You log when you presume that that particular data may be affected by inflation. So let's take your salary like this. If you look at your salary, could it be that your salary could be affected by inflation? Could your salary be affected by inflation? I'm asking you.
Yes, yes.
Good. Could your pregnancy be affected by inflation?
Hey, no.
Exactly. So you see, your brain can quickly tell you whether something could be affected by inflation or not. And once you have the belief that it may be affected by inflation, then that variable may be logged. But the order of the logging is this. You log the dependent variable first. You don't log the independent variables. Then one by one, you start logging the independent variables and you run. After each case, you run the regression to see what will happen. After each case, you run the regression to see what will happen. You keep adding to the logging until you have several models. And on the basis of that, you will check which one gave you a better R-square, a more significant estimate. And then you can select. Asad, you get a question.
Yes, Prof.
So that's how you go around it. And some of you will have to be doing similar thing like that. And that is how it got to be. Next question. So logging should not be done for musicality. It should be supported. It should be backed by, a priori knowledge. It should be backed by even the literature that you are reading. Okay? You should back it. You should have a backing for that. Yes, Fosun. Dennis.
So Prof, in reviewing a literature, should the author write what the R squared was before logging and after? Or
sorry, say that again.
I mean, if in reviewing the literature, should the author state what the R squared was before the log transformation happened? Should it be before and after? Should it state both R squared? Or just stating the R squared after logging is okay?
Oh, tell us before and after. If I didn't hear a question well, but if I did, what I'm saying is that the person should tell us the before and after.
The person just didn't state that I log transformed and this is the R squared. He should have told you what the R squared was before the log transformation happened.
Oh, it's not necessary. If he says that he log transformed it, then there was an R squared before, so there's no need necessarily for him to tell you. But if the person has even said I log transformed it, that's okay.
Okay, Prof.
Don't punish the person for telling you. If the person doesn't tell you at all, that's where the problem is. Next question. I'm sure you're all fine. Let's look at there are three more statistics. Sorry, there are three more diagnostics we have to look at. I'm not going to look at them today. I'll look at them next time. But before then, there's one particular thing I want to talk about, which is not really speaking a diagnostic check, but you have to still kind of have a look at it. Okay. So like I'm saying, before, okay, hold on. All right. So before we check for heteroscedasticity and autocorrelation, there are other factors, though they are not assumptions, that we have to check. Influential variables. Influential variables. Okay. We will not look at heteroscedasticity and autocorrelation today. They are big topics. Okay. But influential variables, I'll refer you to some websites for you to check. Look at influential variables. What is the difference between an outlier and an influential variable? Influential variable are observations that exert undue influence on the estimate. You can be an outlier, but you are not an influencer. All influential variables are outliers, but not all outliers are influencers. And there are many approaches you can use to check whether your data has gotten some outliers. Outliers simply means they have large residuals. And whether they are influential variables. Influential variables means that if you remove them, they will substantially affect the result. So influential variables is a combination of leverage and outlierness. And there are two ways you can check for outliers. One, you can use residuals. Two, you can use leverages. Three, you can use Cook's distance and defects. Okay. Let's look at one of them. Let's check whether there are outliers in the Brukutu data set. Okay. So let's go to the data set and follow me here. This is simple. Okay. Outliers. Run this model, which is the car, and then let's put this in four-dimensional space. Let's plot this. We've seen this before. This is the residual plot. And it can, do you remember we detected outliers some minutes ago? Okay. We were able to detect outliers. Okay. And you can see that there are some observations that may prove to be outliers. Observation number what? Observation number what? Here it appears that only observation number 24 and 14. They are not too clear. So let's go to another plot. Another plot is to use the AV plot. I'm having the AV plot here. Let's run that. Look at that. The AV plot will tell you for each independent variable, you are able to see the AV plot, the added variable plot, and you can see which variable seems to be popping as an outlier. Which variables are those? Sorry, which observations? You can tell. Which observations are proving to be outliers?
Mm. 17 and 24.
And which other one?
24.
Yes, and which other one?
I mentioned 17 earlier.
Yes, 17 and 24. And which other one? If you check the models carefully, there are some 20. One or two more.
25.
There is also 25
and 26.
Good. Now you are seeing more. Eh? So that's it.
Yeah.
So these are possible outliers. Okay. Now look at this. So you can see that we have these possible outliers in the data. Let's look at so we can check whether which variables are showing some possible outliers. We can check that. We can do this outlier test and look at the command here at the bottom here. The outlier test can be done here. And when you look at the outlier test, something is happening. It's called the Bonferroni test for outliers. If the unadjusted p-value is less than 5%, then there may be an outlier. And it will flag the name of the outlier, that observation. Ours, which observation has been flagged? $14. Okay, 14. But the p-value is not available. So the first, let me foresee circling it. That's good, because you can circle. Okay. So ours is that 14, but the p-value of it shows that it's not a big problem. The p-value is 7.3% or 7.4%, which shows that it is even fine. Okay. So really, it's not a big of an influential variable. Only when an observation has a high leverage, take note, and is an outlier, is when we say that that variable is an influential variable. There are other ways you can check for the influential variable. Ours, we are not detecting much. We are not seeing much of it. You can use bubble plot here. Okay. This bubble plot will tell you possible influential variables and whether they are big issues. The bigger the bubble, okay, the bigger the bubble, the bigger the hubble. That's what I say. The bigger the bubble, the bigger the bubble. Okay. And so you can tell from this. And then you can use this command 204 to summarize possible influential variables. And none of them, this last command tells you that potential influential variables, there's none. Okay. You can see that in the result. None of the variable is a potential influential observation. So we can conclude and say that there is not much situation there. Okay, so let's assume that there is not much problem. Or even if there is, how do you handle it? If there is, one way you handle it is to use something called robust regression. If there is, or there are possible outliers, use robust regression. Run the foreign command and then the mass command, and then run this robust regression. This is our last command we are running here. Robust regression. This command here, R gene multi, robust gene multi. Just run that. And this is it. Okay. So having run this robust regression, you can now use that to determine if there are bigger issues with the outliers. And that's it. You can use this one to represent the new standard errors. And then the estimate and the standard error. You will see some beautiful things that are happening, to be honest with you, okay? Showing the relationship with some of the variables here. Robust regression can be used to handle presence of outliers. Okay. Ladies and gentlemen, at this stage, in fact, you can use a certain command. I don't want to go to that command yet. Let me see. You can use a certain command that will tell you about each of these things that we saw, whether they are problems or not. We'll look at that one next time. So what I have done is that I've concluded with how to detect outliers, how to detect influential observations, and if they are there, how to handle them with robust regression. Okay. So these are the ways, some of the diagnostics that you can do when you're undertaking a regression. There are a few more diagnostics that we got to do, not today. The first one we'll do next time, where is that? The first one we are going to do next time is known as heteroskedasticity. And then the final one we shall look at is autocorrelation. And then when we get to panel data models, we'll handle endogeneity problem. Any question? Any question? Please go and watch this video again. Gives it a thumbs up If you like it, give it comment, ask questions there, so that I will use that as a way to judge your understanding power.